Welcome to this problem walkthrough. In this session, we'll dive into problem number 314, titled Binary Tree Vertical Order Traversal. We'll break down the problem, explore different approaches, and understand the optimal solution step by step. Let's get started. In this problem, we are tasked with performing a vertical order traversal of a binary tree. Vertical order traversal involves grouping nodes based on their vertical columns, which are determined relative to the root node. The root node is at column 0, and as you move to the left child, the column decreases by 1, while moving to the right child increases the column by 1. Within the same column, nodes are further sorted by their depth, meaning nodes higher up in the tree are considered before nodes lower down. Additionally, if multiple nodes share the same column and depth, they are ordered from left to right based on their position in the tree. The final output is a list of lists, where each sublist contains the values of nodes from the same vertical column, listed from the leftmost column to the rightmost column. The input consists of the root of the binary tree. This root is represented as a binary tree node object, where each node has three properties: val, which is an integer value representing the node's data; left, which is a reference to the left child node, or null if no left child exists; and right, which is a reference to the right child node, or null if no right child exists. For the output, we return a list of lists. Each sublist contains the integer values of all nodes from a single vertical column. The nodes in each sublist are ordered as per the rules of vertical order traversal, by depth, and within the same depth, by their left to right order in the tree. Let's look at an example to clarify this. Consider a binary tree where the root node is 3, with 9 as its left child and 20 as its right child. Node 20 further has two children, 15 on the left and 7 on the right. For the output, nodes are grouped by their vertical columns. Column -1 contains node 9. Column 0 contains the root node 3 and node 15, with 3 appearing first as it is higher in the tree. Column 1 contains node 20, and column 2 contains node 7. Therefore, the vertical order traversal for this tree is 9, 3, 15, 20, 7. Now consider another example. In this case, the root node is 1, with 2 as its left child and 3 as its right child. Node 2 has two children, 4 on the left and 5 on the right. Node 5 further has two children, 6 on the left and 7 on the right. Grouping nodes by their vertical columns, column -2 contains node 4. Column -1 contains node 2. Column 0 contains nodes 1, 5, and 6, with 1 appearing first because it is the highest in the tree. Column 1 contains nodes 3 and 7. Thus, the vertical order traversal for this tree is 4, 2, 1, 5, 6, 3, 7. Finally, let's discuss the edge cases. If the tree is empty, meaning the root is null, the output should simply be an empty list. For a tree with only a single node, the output will contain a single sublist with that node's value. In the case of a skewed tree, where all nodes are either to the left or to the right, the output will reflect the linear vertical order of the nodes. These constraints and edge cases ensure that our solution handles all possible scenarios, from the simplest to the most complex. When tackling the problem of binary tree vertical order traversal, one possible approach to consider is a brute force method. The intuition here is to traverse the tree level by level while manually calculating the column index of each node based on its position relative to the root. During this traversal, we would group nodes into separate lists according to their column indices. Once all nodes are processed, we would sort these column indices and return the nodes in the order of their columns. While this approach is conceptually straightforward, it comes with significant inefficiencies. Sorting the column indices adds unnecessary overhead, and the process of manually tracking column indices can become quite cumbersome. In terms of complexity, this approach runs in n log k time, where n is the number of nodes and k is the number of unique columns, with additional space requirements for storing the nodes and their column indices. Ultimately, this method is not optimal due to the overhead of sorting and the convoluted column indexing process. Now, to address the inefficiencies of the brute force method, we can turn to an optimized approach that utilizes breadth-first search, or BFS, combined with a hash map. The key insight here is to use BFS for its natural ability to traverse nodes level by level, ensuring we preserve the vertical order of nodes. Instead of manually sorting column indices, we use the hash map to group nodes dynamically by their column indices during traversal. Each column index is determined incrementally. Moving left decreases the column index by 1, while moving right increases it by 1. BFS ensures that as we process nodes, we append them directly to the appropriate column group. By employing a tree map or an ordered dict, we can maintain the column indices in sorted order without needing a separate sorting step. The steps are straightforward: initialize a queue with the root node and column index, update the hash map as we dequeue and in-queue nodes, and finally extract the results in sorted column order. This approach is both time efficient, with O(n) complexity, and space efficient, requiring storage for the queue and hash map. The optimized BFS approach offers several key advantages. First, it eliminates the need for post-processing or sorting column indices, which significantly simplifies the implementation. Grouping nodes and retrieving them in order is both efficient and straightforward. Another potential method is a depth-first search, or DFS, with column tracking. While DFS can achieve vertical traversal by tracking column indices recursively, it has its own challenges. Specifically, DFS does not inherently guarantee level order, so additional processing is required to sort nodes within each column by their levels. This sorting step increases the time complexity to O(n) log k, and the recursion stack adds to the space complexity. As a result, DFS is less efficient and more complex to implement compared to the BFS approach. While it's a valid alternative, it lacks the simplicity and performance benefits that BFS provides for this particular problem. Given the options, the chosen strategy for solving the binary tree vertical order traversal problem is the optimized BFS with a hash map. This approach leverages BFS to handle level order traversal naturally, ensuring that vertical ordering is maintained without requiring additional sorting. The hash map provides an efficient mechanism for grouping nodes by their column indices, making the process both intuitive and streamlined. This method achieves optimal time complexity of O(n), while maintaining simplicity in implementation. While DFS could also work, it involves additional sorting to maintain level order, which makes it less efficient. Similarly, the brute force approach introduces unnecessary overhead due to sorting and manual column indexing. The aha moment came from realizing that BFS inherently preserves level order, allowing us to avoid extra bookkeeping for node levels and simplifying the solution dramatically. In summary, the BFS with hash map approach strikes the perfect balance between clarity, efficiency, and ease of implementation, making it the ideal choice for this problem. To tackle the problem of binary tree vertical order traversal, we first need to understand the concept of column indexing. The root node starts at column 0, its left child is in column -1, and its right child is in column +1. This pattern continues for all descendants, where left children decrement the column index and right children increment it. The task is to group nodes by their column indices. To achieve this, we use a breadth-first search traversal. BFS is ideal because it processes nodes level by level, which aligns well with the problem's requirements. During traversal, we associate each node with a column index and use a dictionary to group nodes by these indices. The algorithm begins by initializing a queue for BFS and a dictionary for storing the column-wise node groupings. The root node is added to the queue with its column index of 0, and we proceed from there. As we begin the BFS traversal, we repeatedly dequeue the front element from the queue. This element includes the current node and its associated column index. The node's value is then added to the corresponding column in the dictionary. If the node has a left child, it is enqueued with a column index decrement by 1. Similarly, if the node has a right child, it is enqueued with a column index increment by 1. This ensures that each node is correctly grouped based on its vertical alignment. Once the BFS completes, the dictionary will contain all nodes grouped by their column indices. To prepare the output, we sort the column indices, ensuring the result is ordered from the leftmost column to the rightmost. Finally, we extract the node values from the dictionary in this sorted order to produce the desired vertical order traversal. It's also essential to think about edge cases, like empty trees, which should return an empty result, or trees that only extend in one direction, which would form a single chain of columns. The dictionary plays a key role in this solution, enabling efficient grouping and retrieval of nodes based on their column indices. Sorting the column indices at the end ensures that the output is correctly ordered from left to right. The two primary data structures used are the queue and the dictionary. The queue facilitates the BFS traversal, storing tuples of nodes along with their column indices, ensuring we process nodes level by level. Meanwhile, the dictionary maps column indices to lists of node values, allowing us to efficiently group and access nodes by their vertical alignment. In terms of complexity, BFS visits each node once, resulting in a time complexity of O(n), where n is the number of nodes. Sorting the column indices contributes an additional O(k*log k), where k is the number of unique columns. Since k is typically much smaller than n, the overall time complexity is O(n plus k*log k). For space complexity, the queue requires O(w), where w is the maximum width of the tree, and the dictionary requires O(n) to store all nodes, resulting in a total space complexity of O(n). The BFS traversal is particularly memory efficient compared to a depth-first search, where the recursion stack could grow to the tree's height. By sorting the column indices only once at the end, we avoid redundant operations during traversal. To better understand this algorithm, let's consider a specific example. Imagine a binary tree where the root node is 1, with left and right children 2 and 3, respectively. Node 2 has children 4 and 5, while node 3 has a single right child, 6. This structure will guide us as we walk through the algorithm step by step, observing how nodes are grouped by their column indices during the BFS traversal. We start the BFS with the root node, 1, at column 0. The queue initially contains just this node, and the dictionary is empty. Processing node 1, we add its value to column 0 in the dictionary and enqueue its children, node 2 at column -1 and node 3 at column 1. Next, we process node 2, adding its value to column -1 and enqueuing its children, node 4 at column -2 and node 5 at column 0. Moving on to node 3, we add its value to column 1 and enqueue its child, node 6 at column 2. This process continues until the queue is empty. At the end, the dictionary contains the following groups: column -2 with 4, column -1 with 2, column 0 with 1, 5, column 1 with 3, and column 2 with 6. Sorting the columns and extracting their values gives the final output, 4, 2, 1, 5, 3, 6. This implementation solves LeetCode problem 314, binary tree vertical order traversal, using a breadth-first search (BFS) approach. Let's break down the solution step by step. First, we import deque and defaultdict from the collections module. Deque is used for BFS traversal, and defaultdict helps in grouping nodes by their column indices efficiently. The vertical order function begins by handling the edge case where the root is none. If the tree is empty, the function returns an empty list. Next, we initialize two data structures. 1. Column_table, a defaultdict where each key represents a column index, and the value is a list of node values belonging to that column. 2. Queue, a deque initialized with the root node at column 0. Each item in the queue is a tuple, node, column_index. The BFS loop starts by dequeuing the first node. If the node is not none, its value is appended to the list corresponding to its column in column_table. Then, the left child of the node is enqueued with a column index decrement by 1, and the right child is enqueued with a column index increment by 1. This process continues until the queue is empty, ensuring that all nodes are processed level by level and grouped by their column indices. Finally, the column_table keys, column indices, are sorted, and the corresponding node value lists are extracted as the result. The algorithm is efficient, with a time complexity of O(n), where n is the number of nodes in the tree. This is because each node is processed exactly once. The space complexity is O(n) as well, due to the storage requirements of the column_table and queue. This solution ensures that nodes are traversed in vertical order and grouped correctly by their column indices, fulfilling the problem's requirements effectively. Here, we start with the implementation of the vertical order traversal in Java. First, we import the necessary classes from the Java standard library, including utilities like map, queue, and list. Inside the solution class, we define the main method, vertical order, which takes the root of the binary tree as input. If the root is null, we immediately return an empty list since there's nothing to traverse. Next, we initialize a hash map called column_table to group nodes based on their column indices. This map will help us store lists of node values corresponding to each column. A queue is used to perform a breadth-first search, where each element in the queue is a pair consisting of a tree node and its associated column index. We begin by adding the root node with a column index of 0 to the queue. Additionally, we define two variables, min column and max column, to keep track of the smallest and largest column indices encountered during the traversal. Now, as long as the queue is not empty, we repeatedly process its elements in a loop. For each node, we retrieve its value in column index. If the node is not null, we ensure the column table has an entry for the current column, and then we add the node's value to the corresponding list in the map. Next, we update the min column and max column variables to reflect the new range of column indices if necessary. This ensures we keep track of the leftmost and rightmost columns encountered so far. After that, we add the left and right children of the current node to the queue. The left child gets a column index decrement by 1, while the right child gets an index increment by 1. This way, we maintain the correct column positions for all nodes as we traverse the tree. Once the queue is empty, meaning we've processed all nodes, we move on to building the final result. We create a new list called result, which will hold the lists of node values grouped by their column indices in ascending order. Using a for loop, we iterate through the columns from min column to max column. For each column index, we retrieve the corresponding list of node values from the column table and add it to the result list. Finally, we return the result, which now contains the vertical order traversal of the binary tree. To support our implementation, we define two helper classes. The first is the treeNode class, which represents each node in the binary tree. It includes fields for the node's value, left child and right child, along with 3 constructors for different initialization scenarios. The second helper class is the pair class, which we use to store key value pairs in the queue during the breadth-first search. This class has 2 fields, key and value, and provides a constructor for initializing these fields. Additionally, it includes getter methods, getKey and getValue, to access the key and value of a pair object. These helper classes provide the structure and functionality needed to implement the vertical order traversal efficiently and cleanly. To solve the problem of performing a vertical order traversal on a binary tree, we begin by initializing 2 key components. The column_table is a dictionary that will store nodes grouped by their column indices, and the queue is initialized with the root node and its column index. In this case, the root node is 3, which starts at column 0. Using a breadth-first search approach, we process the root node first. After popping 3, 0 from the queue becomes empty temporarily. We add the value 3 to column_table 0, so the table now looks like 0, 3. Next, we add the left child 9 at column -1 and the right child 20 at column 1 to the queue. At this point, the queue contains 9, -1, 20, 1, and we are ready to process the subsequent nodes. Now, the next node to process is 9, which is at column -1. After popping it from the queue now contains only 21. We add 9 to column_table -1, so the table is updated to 0, 3, -1, 9. Since node 9 has no children, nothing further is added to the queue. Then, we move on to process node 20, which is at column 1. After removing it from the queue temporarily becomes empty again. We add 20 to column_table 1, making the table 0, 3, -1, 9, 1, 20. Node 20 has 2 children, 15 at column 0 and 7 at column 2. These are added to the queue, which now contains 15, 0, 7, 2. Next, we process node 15, which is at column 0. After popping it from the queue, we add 15 to column_table 0, updating the table to 0, 3, 15, -1, 9, 1, 20. Finally, we process node 7 at column 2. After removing it from the queue, we add 7 to column_table 2. The table now becomes 0, 3, 15, -1, 9, 1, 20, 2, 7. At this point, all nodes have been processed, and the column_table is populated with nodes grouped by their respective columns. The next step is to sort the column indices to ensure the correct vertical order. Extracting the columns in sorted order gives -1, 0, 1, 2. Using this order, we format the results by retrieving the node values for each column, resulting in the final output 9, 3, 15, 20, 7. Now, let's consider another example, where the tree consists of only a single node. Here, the tree contains just the root node 1. Again, we initialize the column_table and the queue, starting with the root node at column 0. When processing the root node 1, we pop it from the queue, which then becomes empty. We add 1 to column_table, 0, resulting in 0, 1. Since there are no other nodes in this tree, the next step is to sort and format the results. Extracting the columns in sorted order gives 0, and the final output for this single node tree is 1. Moving on to a more complex example, we have a larger tree with the root node 1, which has 2 children, 2 on the left and 3 on the right. Node 3 further branches out to nodes 4 and 5, and node 4 has an additional left child 6. As usual, we start by initializing the column_table and the queue. The queue begins with the root node 1 at column 0. The first node to process is the root node 1. After removing it from the queue, we add 1 to column_table, 0, so the table becomes 0, 1. Then, we add its left child 2 at column-1 and its right child 3 at column 1 to the queue. Next, we process node 2, which is at column-1. We add 2 to column_table, -1, updating the table to 0, 1, -1, 2. Since node 2 has no children, we proceed to node 3, which is at column 1. Adding 3 to column_table, 1, updates the table to 0, 1, -1, 2, 1, 3. Node 3 has 2 children, 4 at column 0 and 5 at column 2. These are added to the queue. Now, we process node 4, which is at column 0. Adding 4 to column_table, 0, updates the table to 0, 1, 4, -1, 2, 1, 3. Node 4 has a left child 6, which is added to the queue at column-1. Then, we process node 5, which is at column 2. Adding 5 to column_table, 2, updates the table to 0, 1, 4, -1, 2, 1, 3, 2, 5. Finally, we process node 6, which is at column-1. Adding 6 to column_table, -1, updates the table to 0, 1, 4, -1, 2, 6, 1, 3, 2, 5. With all nodes processed, we sort the column indices to get -1, 0, 1, 2. Using this order, we format the results by retrieving the node values for each column, resulting in the final output 2, 6, 1, 4, 3, 5. This completes the vertical order traversal for the given complex tree. To analyze the time complexity of the binary tree vertical order traversal algorithm, we start by breaking it into its key components. First, the breadth-first search, or BFS, processes every node in the binary tree exactly once. If the tree contains n nodes, this means BFS contributes O(n) to the time complexity because each node is visited just once. Next, during the traversal, we update the column table by inserting each node's value into a dictionary-like structure based on its column index. Since this operation is O(1) per node and is performed for all n nodes, it also contributes a total of O(n). Finally, after the traversal completes, we need to sort the column indices to ensure the output is in the correct order. If there are k unique column indices, this sorting step takes k*log k. In the worst-case scenario, such as in a highly skewed tree, k can approach n, making this step contribute n*log en. Together, these steps form the basis for the time complexity analysis. Now, combining all these steps, the overall time complexity can vary depending on the specific structure of the binary tree. In the best or average case, where the number of unique columns k is relatively small compared to the total number of nodes n, the complexity is n plus k*log k. However, in the worst case, when k approaches n, the total complexity becomes n*log n. Moving on to the space complexity, we start by considering the queue used for BFS. This queue holds tuples containing a node and its column index. In a balanced binary tree, the maximum number of nodes at any level corresponds to the tree's maximum width, which can be n in the worst case. On the other hand, in a skewed tree, the queue size at any time is only 1, as there is just one node per level. Therefore, the queue's space usage depends on the tree's width, with an upper bound of n. Additionally, we must account for the space required by the column table. This structure stores a list of nodes for each column index, and in the worst case, it requires O(n) space for the values. The keys in the column table, representing the unique column indices, take up O(k) space. Since the maximum number of unique columns k can reach n in a skewed tree, the column table's total space requirement becomes O(n). Combining these components, the overall space complexity of the algorithm is dominated by the queue and the column table, both of which require O(n) in the worst case. As a result, the total space complexity is O(n), which is efficient given the problem constraints. When comparing this optimized approach to a brute force method, the difference in efficiency is quite clear. A naive approach might involve multiple traversals of the tree, grouping nodes by column indices, and sorting nodes within each column. This results in a much higher time complexity of O(n) squared, due to repeated traversals and redundant computations. In contrast, the optimized solution leverages BFS and a hash table to minimize these inefficiencies. By visiting each node exactly once and sorting only the column indices, the worst-case time complexity is reduced to O(n*log n). The mathematical justification lies in the dominance of the sorting step, which is bounded by O(n*log n, while the BFS traversal contributes just O(n). Moreover, the space complexity is linear, i.e., O(n), as the algorithm uses only the necessary data structures to store nodes and column indices. This combination of efficient time and space usage makes the optimized solution significantly better than naive methods for vertical order traversal of a binary tree. When solving the binary tree vertical order traversal problem, there are a few common mistakes to watch out for. First, incorrect column index calculation is a frequent issue. For instance, when traversing the tree, you need to decrement the column index for the left child and increment it for the right child. If you fail to do this properly and update both directions the same way, the nodes will overlap or end up in the wrong columns, which breaks the traversal logic. Another mistake is failing to account for negative column indices, particularly in left-heavy trees where indices can extend into negative values. If your solution relies on fixed-size arrays or doesn't handle negative indices gracefully, it can lead to indexing errors. Finally, some solutions overlook the need to sort nodes within the same column when they share the same row. This is critical because the output must often adhere to a specific sorting rule, like node value or insertion order. Neglecting this requirement leads to inconsistent or incorrect results. Additionally, the choice of data structures plays a significant role in the efficiency of your solution. Using a simple list or dictionary instead of optimized options like default dict or ordered dict can unnecessarily increase the complexity of insertions, lookups, and sorting operations, making your solution inefficient for larger trees. Another common pitfall is misunderstanding the problem requirements entirely. For example, some candidates confuse vertical traversal with other traversal patterns like level order or zigzag traversal. This misunderstanding often results in implementing the wrong algorithm, which wastes valuable time, particularly in interview settings. Always take a moment to carefully analyze the problem statement before diving into the implementation. To approach vertical order traversal problems effectively, there are a few key insights worth noting. First, these problems require a strong understanding of how to map tree nodes to specific columns and rows. This often involves using BFS or DFS, paired with metadata like column indices. An optimization tip here is to use a default dict to map column indices to lists of nodes. This simplifies the grouping process during traversal, leaving any necessary sorting until after the traversal is complete. It's also helpful to think of these problems as projecting nodes onto a 2D grid, where the vertical and horizontal positions of nodes determine their placement. Recognizing this pattern can help you structure your solution faster. Finally, remember to test edge cases, such as a single node tree, left-skewed or right-skewed trees, and trees with duplicate values. These scenarios often reveal weaknesses in your approach. There are several related problems that you might encounter, which build on similar concepts. For example, LeetCode 987, vertical order traversal of a binary tree, is a more advanced variant that specifically requires sorting nodes within the same column. In contrast, LeetCode 314, binary tree vertical order traversal, focuses on level-wise vertical traversal without additional sorting. Another related problem is LeetCode 103, binary tree zigzag level order traversal, which involves alternating the order of nodes at each level, adding another layer of complexity. Finally, LeetCode 199, Binary Tree Right-Side View, has you identify the rightmost node at each level, showcasing a similar traversal pattern using BFS or DFS. Practicing these problems can help you recognize recurring patterns and improve your problem-solving speed. When it comes to alternative approaches, two primary traversal strategies often come into play, BFS and DFS. Using breadth-first search, you can traverse the tree level by level while tracking column indices with a queue. This method is particularly intuitive for level-order traversal, though it may require additional sorting once all nodes are processed. Depth-first search, on the other hand, involves a recursive approach, where you pass column and row indices as arguments to maintain tracking. DFS offers more direct control over the traversal order but requires careful management of recursion depth to avoid stack overflow in deep trees. Another alternative is pre-processing column indices to normalize them. For example, if the smallest column index is negative, you can shift all indices to start from 0. While this simplifies output formatting, it adds pre-processing overhead, so it's a trade-off to consider depending on the problem constraints. Great job! In summary, we tackled the binary tree vertical order traversal problem and learned how to use a hash map for efficient column tracking. Remember the importance of understanding traversal techniques and leveraging the right data structures. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!